the friction stir processing, then I will go to materials and methods, then I will explain about my experiments, results, and final conclusion. So, friction stir processing is based on friction stir welding, which was invented in 1991 by TWI, UK. It is a solid state process, and the energy input and the distortion are significantly less in this process, so we get less effect and improve the material properties. This is the schematic of process. In this process, this is the base plate where we do the processing, and this is the tool we use. This tool is made up of high-speed steel and carbide. It depends on the application and material. So this tool rotates at high RPM according to our requirement, and this is the tool pin which goes inside the material, and after some time this tool will traverse throughout the material, and these are the 4 zones which we will get after the processing. The center zone is the stir zone, where we will get highest mixing, and beside this zone we have this TMA, thermomechanical affected zone, and beside this we have heat affected zone, and after this we have this base material. I will show this process using this video clip. So this is the tool, and this is the material. This tool goes inside the material at certain RPM, and there is a dwelling time for this process. And after some time, this is the solder. When this solder touches this material, there is a friction. So because of this friction, heat generates. And after this tool will traverse on the axis of the welding. So after this, we get this type of thing. Okay. So what are the advantages of this process? The advantage of this process can be used for all materials, and the main advantage of this process is it is in the solid state. There is no melting in this process, so we don't get more defects, and we have finer grains in the material and more stress in the material. So I will come to the experimental things. I used copper as the matrix material, and SiC and ceramics is the reinforcement, and using this process. So this is the schematic of preparing the composite material by using this process. This is the base plate, matrix plate. It depends on the thickness. I used the 6 mm thickness plate, and we made these holes on the plate and this groove to fill the reinforcement in the material. And this is the machine we have designed in the lab, where I did all experiments. This is the microstructure. This is a very good microstructure of copper matrix, and this is the mechanical properties before processing of the base metal. We had 8 THV hardness and 240 MPa resistance. And this is this is SiC and ceramic material which have high temperature stability and which shows high oxidation resistance at high temperature, and it has 2 gram per cc density. This is purely porous. It shows good tribology properties. That's why I use this ceramic material as a reinforcement, and it shows high wear and low wear. This is the experiments which I did. I did multi-pass processing on base copper and both for copper component also. And these are the parameters which I used. The tool was rotating at 1000 rpm, and the traverse speed was 40 m per minute, and there is a tilt angle in this process which was 2 degrees. And after processing, this is the image of pure copper processing, and this is the image of composite processing. And this is the load with timing, how the load varies with time. So when the tool goes inside, there will be a low load, but when the shoulder will touch the surface of the material, there will be high. After that, when it will traverse, it will be a constant. After that, it will drop. So on the same material, I cut the samples from this sturgeon for doing the wear experiments. So this is the setup which I used for doing wear experiments. These are the experimental conditions which I used. Load was constant, the distance was 2,000 meter, and I did the experiment in vacuum. The pressure was 3 MPa, and I used an aluminum disc as a counterpart. Now I will come to the discussion part. So these are the properties of processed copper. So I did multi-pass processing on the base material. So it shows after third pass the hardness was high, and in the second pass the hardness was low because of softening take place in the process. And the yield strength and UTS also was not increasing much in the base material. These are the optical micrographs which I had after. This is the composite processing. So this is the composite zone where we get mixing of the reinforcement, and these are the optical microscope images where we can see the particle distribution in the matrix. And this is the flow pattern of reinforcement in the base metal. These are the SEM images of composite which I took after processing from the same places. So this is secondary images. This is BAC image. This is topographical images. So from these images we can confirm that the particles are distributing properly and uniformly, and some particles are big, we can see. But when we used FESEM, then we found out that particles are mixing in nano level also in the range of 100 to 200 nanometer. After that, we did the EDS analysis to confirm that whether those particles are ceramic particles or not. So after that, we confirmed that those are ceramic particles which are there in the matrix. Then for more confirmation, we did color mapping of particles from the same samples. So this is base copper, where we can see the copper in this color here, and this is for SI, where we can see this SI particles, carbon particles, and nitrogen particles. After that, we did micro hardness mapping for the sample from top to bottom, how it varies from top to bottom. So we got this micro hardness around 224 HV from top to bottom, which was 3 to 4 times compared to base metal. And this is the graph for yield strength UTS. After this, we got the result from wear testing, which shows that there was a less wear in composite compared to base metal. And the variation of coefficient of friction, initially it was high in the composite, but after that the coefficient of friction was less compared to pure copper and processed copper. Now I will come to conclusion. After that we conclude that these coppers SiC composites were successfully made by FSP, and increase in hardness in FSP copper was due to grain refinement, and the presence of hard particles in the composite. And regarding that the results of wear, we were expecting that decrease in coefficient of friction in the composite was expected due to the formation of thin lubrication film. And in the base copper and processed copper, it was due to formation of thicker film. And the addition of these ceramic particles was responsible to improve the wear and shear resistance when we compared to the base metal. With this, I thank you all.
Thank you, Mr. Ajay Kumar. I give a last word for Mr. Kumar G.H. and Benny Thomas from Gas Turbine Research Establishment, DRDO, Ministry of Defense, Bangalore, India. If not, then the session is open for question and answer. If anybody is having any question can be raised.